You can see here that we have 3 services running: the web demo application, the geocoder, and the geoenrichment modules, each with their own single instance. You can see on the left that there is currently no load on the system, although it is set to auto-scale when the load on the system exceeds 50%. So let's see what happens when we apply a heavier workload. We've configured the tool to read a set of records from an input file. We will be using 160 threads over a ramp-up time of 30 seconds, and the tool will kick off a number of concurrent geocoding requests using addresses read from the input file. You can see that the HTTP requests are unique and being generated from the input file, with each request and response posted in JMeter's results tree. You can see that all 160 threads have been started in the first 30 seconds. You can see how the workload increase is resulting in more pods being added to the Kubernetes cluster. As the 50% resource threshold is exceeded, more pods are spun up to support the increased demand. On the right, you can see the requests being made to Kubernetes for more pods to be started. Although there is a slight latency to the requests as the nodes get started, the overall impact is minimal. The increase in the number of transactions being processed corresponds to the number of replica pods created by Kubernetes to support the active workloads. You can see that the graph shows dips in processing performance, where pods are being started to support the demand for geocoding services. Notice how the system can sustain an active workload for a long period of time. This could be minutes, hours, or even days. The graph also shows the demand for geocoding services drop-off pods are shut down and deallocated. The JMeter aggregate graph shows that most of the API requests complete very quickly, and the total number of concurrent requests can be accommodated through the auto-scaling feature. In the case of this test, the average request latency is under 50 milliseconds. This is somewhat skewed by the latency associated with the requests that forced the autoscaler to spawn the additional pods, waiting for the pod to start and become ready to accept requests. Notice that 90% of all requests returned is under 50 milliseconds. Notice that as the number of API requests declines and the load on the pods falls below 50%, Kubernetes will automatically start to shut down the pods.